Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And we're going to be talking about something called storm relative motion. And this is a very important concept when it comes to thunderstorms, especially severe thunderstorms, because if you simply take a look at the storm from the standpoint of the environment, then you don't see all the details. And if you take a look at it from the storm's perspective, okay, then it gives you a very different answer. And so that's what we're going to talk about today. So let me put myself down here in the corner, and we're going to be taking a look at, again, the wind that the storm experiences, okay? The storm is moving along in the flow, but if you take out the movement of that storm, okay, the flow that it's embedded in, then you see how the storm is actually experiencing the environment, and that's what we actually want to look at. So you subtract the storm motion from the wind at any given level to get the storm relative wind at that particular level, okay? And if you're in your car traveling at 60 miles per hour and you put your hand out the window and tilt it a little bit, you know, so that it's facing forward, then you're going to feel wind against your hand, and that wind is being generated by the fact that the car is moving at 60 miles per hour, okay? There may not be any wind out there at all if you're just standing still, but if you're moving, then it's a whole different ballgame. And so that's sort of the concept that we're looking at here. So I'm going to show you something called a hodograph, and this is something that was actually used quite a bit, I guess, back in the 40s and 50s, sort of fell out of favor, and then people realized, the research community realized that, hey, we need to take another look at this, and so it's very widely used now, especially when it comes to severe weather. So we're going to put a little x-axis and a y-axis there, and what we're going to do is take 3 levels of the atmosphere, okay? So this first dot represents the surface wind, okay? So I'm going to draw an arrow from the middle where those 2 axes intersect to that dot. So in this case, the wind would be coming from the southeast, let's say at about 10 miles per hour, okay? Now, let's go to the next level. And here we have maybe a southwest or south-southwest wind at maybe about 20, maybe a double or a little bit more than double what the surface wind is. And then finally, we have a southwest wind at, let's say, 30 or 35 up at the 3rd level, okay? Now, this is going to translate into what we call a straight hodograph, okay, where you connect those dots at the end of those arrows, and this is what you get. Now, for tornadoes, typically we want to see a curved hodograph where there's more wind shear going on here, not only in terms of direction, but also speed. But for simplistic purposes, I just took the simplest example I could find, and so in this particular case, we have a straight hodograph. Now, the thunderstorm is going to move with the average wind over this entire layer, all the way from the surface up to that 3rd level where the 3rd dot is, okay? And with a straight hodograph, you can basically assume that the mean wind, or the average wind, is about at that middle dot, okay? So as a result, I made the arrow a little thicker there. That is the mean storm motion, okay? So what we want to do is now move the entire coordinate system so that it is at the end of that arrow, okay? And now we redraw those arrows to those 3 dots, and that gives us what the storm relative wind is at each one of those positions, okay? So the first one, instead of being a southeast wind at maybe 10 miles per hour, now becomes a northeast wind, okay? And in the middle dot, you wouldn't have any relative wind at all. And then on the 3rd dot, the wind would be out of the southwest, okay? So by subtracting out the storm motion, then you get an entirely different answer. And with regard to thunderstorms, you're always focused on the inflow, the low-level inflow of moisture. And so if you can generate more inflow into the storm by this process that you're looking at here, then that is very important in terms of that thunderstorm's development, okay? So the storm relative motion is very critical in assessing severe weather potential. Now, this is another example of this concept, and I'm afraid that I'm going to do a lousy job of explaining this, but we'll give it a shot. So here we have a hurricane, and let's say the winds are blowing 120 miles per hour on the east side of the hurricane and 80 miles an hour on the west side. So the winds are going in a counterclockwise manner like this around the hurricane. Now, just a caution, if you ever hear someone say, oh, well, they're saying that the maximum sustained winds are 100, but it's really 120 because the storm is moving at 20 miles per hour. That's wrong, okay? You can't add to the observed wind. The observed wind is the observed wind, okay? But what you have to do is look at how much wind is the storm generating, and then you add on the movement that it's embedded in, and that's what gives you the observed wind, what the reconnaissance aircraft would find as they're flying through it, okay? So this thing is embedded in a 20 mile an hour flow, okay? Now the problem here is you've got winds from the south here, so the winds with the hurricane are the same direction as the movement of the flow, and over here you've got a north wind, so the two are opposing each other, okay? So if you subtract out the storm motion of north at 20, it's going to decrease this wind here, but it's going to increase this wind here because now you're not fighting it as much, okay? So what you end up with is a storm that is generating 100 mile an hour winds on all sides, but because it's embedded in a flow from the south at 20 miles per hour, because these two winds, both the overall motion that it's embedded in and the wind itself are coming from the same direction, that's going to make the observed wind 120 over here and the observed wind 80 over here, okay? So what the Hurricane Center is not telling you in the advisories, and not that they're doing it on purpose or anything, is they're not telling you how much wind the storm is generating. They're giving you the end result, and the end result is a combination of what the storm is generating plus the flow that it's embedded in, and that's what gives you the observed wind, okay? I hope that makes sense. All right. That is bonus, I forgot I didn't have a slide there. That is bonus weather video number 2 for this week. The next one will be coming up on Friday. Next daily weather update coming up tomorrow. All right, folks, that's it for now. You have a great Wednesday evening, and we'll talk to you again tomorrow. See ya.